In the previous video, we introduced the quantity chi-squared. We achieved this endpoint using a cartoon in which we already knew a function that accurately described a physical experimental system. This is not always a realistic description of research. In this video, we describe how the quantity chi-squared can be applied to the fitting of mathematical functions to data in the more realistic situation in which we lack exact knowledge of the correct theoretical curve and in which we lack exact knowledge of the widths of the distributions from which experimental measurements are drawn. In contrast to the thumbnail at the top left, the big plot to the right contains only sample means and associated error bars. The plot includes neither a theoretical curve nor Gaussian distributions. We appear to lack ingredients that we previously used to write down a probability distribution function describing the likelihood of getting an observed dataset from a given collection of Gaussians straddling a given theoretical curve. To address these two aspects of our ignorance, we make two assumptions. We play pretend in two ways. Suppose our theoretical knowledge amounts to an imprecise guess as to the shape of a curve relating y and x. In this example, we have reason to anticipate a sigmoidal curve, but we do not know the horizontal position x half at which the curve is halfway between its minimum and maximum vertical y values. Additionally, we do not know the minimum y value of the curve, which we call the vertical offset y0. Rather than having a single function drawn confidently as a single bold yellow curve, we have a collection of many possible plots, 5 examples of which are illustrated. In this situation, we say we have a fitting function, which is a vaguely defined curve with geometric features, here x half and y0, which are adjustable so that the function plot can be stretched and distorted to try to imitate a scatter plot of data. A fitting function is a distortable curve. In this example, the fitting function is an adjustable sigmoidal curve. We make our first assumption by pretending that we know that one of these curves is correct and that we know which of these curves is correct. For the time being, let us pretend that this is the curve now drawn boldly in gold. Our second assumption relates to the distributions from which our data are drawn. Pretend that the sample means were plucked from Gaussian distributions with standard deviations exactly equal to the plotted standard errors. Because we are pretending that the solid gold curve happens to be the correct function for describing our experimental system, the Gaussian distributions should be shifted so as to be centered on this curve. We are pretending that the solid gold curve is the correct function, and we are pretending that this collection of Gaussian distributions, whose widths are equal to the widths of the standard errors represented by the error bars, is the source from which our sample means were drawn. Playing pretend in these ways allows us to write down an approximate probability distribution for the vertical displacements of the stars from the solid gold curve, which might actually be different from the vertical displacements of the stars from the accurate curve, and using the standard errors, which might be different from the standard deviations of the actual distributions from which the sample means were drawn. Even though we have pointed out slight differences between the sum of the normalized squared deviations that appears in this exponent and the sum of the normalized squared deviations that we saw in the previous video, we also label this object chi-squared. On this slide, we have discussed the calculation of a chi-squared value using the solid gold curve. The same calculation applied to other curves can provide possibly different additional values of chi-squared and thus possibly different additional values of the probability p of getting the observed data set of stars. Some curves might line up poorly with the stars. We may pretend that one of these curves is the correct function, and we can try to position Gaussian distributions to straddle this curve. We could make this attempt with each of these curves in turn. However, in each case, the observed dataset looks as though it would only rarely arise from the given curve. In these examples, many of the deviations between data points and theoretical curves are large, in the sense that they are noticeably greater than the associated standard errors. For most of the data points, the error bars, those I-beams, fail to thread the chosen theoretical curve. In other cases, curves may line up more closely with the stars. In such a case, the possibility that the chosen curve is correct and that the observed data came from the Gaussian distributions centered upon the curve is more plausible. In this example, it happens that each I-beam threads the curve of interest. The curve we regard as our best answer is the one that most closely hugs the data, in the sense of having the smallest sum of normalized squared deviations, meaning the minimum value of chi-squared. The probability of obtaining the observed dataset, given hypothetically that a particular function plot is correct, is related to the chi-squared value through an exponential and a negative sign. Minimizing chi-squared thus corresponds to choosing the curve for which the probability p of finding the observed dataset would be greatest. This is called maximum likelihood estimation. Our best answer is a curve out of the many possible curves for which it looks most as though the dataset of stars came, so to speak, from the curve. Adjust the parameters until you obtain the curve that makes it most look as though the dataset came from your adjusted curve. This is the curve corresponding to maximum probability, in other words, minimum chi-squared. In this example, x half of star and y naught of star are the parameters that specify the curve that minimizes chi-squared for the particular dataset of stars. Different values of x half could arise when performing fitting, for example, to the set of triangles or to the set of squares. To characterize the variation among values of x half that can be obtained from a large collection of experiments, we describe a procedure that boils down to the quadrature formula of uncertainty propagation. Make the star at x1 jiggle a vertical distance equal to its standard error. The originally measured set of stars is modified by the disturbance of the height of the first star. By momentarily pretending that this modified dataset is itself a dataset to be fit, we can calculate another best fit value of the parameter x half, which potentially differs from the best fit value of x half originally obtained by using the undisturbed set of stars. We can calculate a difference between these parameter values. We can calculate other examples of differences between the best fit values of x half and the undisturbed value of x half by individually jiggling the other stars one by their respective standard errors. Squaring before adding these differences provides a sample estimate S sub x half of star of the standard deviation of the distribution from which the best fit parameter x half of star was plucked. Sample estimates of the standard deviation for y naught are calculated in an analogous way. The equation at the top is an example of the quadrature formula of uncertainty propagation expressed explicitly in terms of differences rather than in terms of partial derivatives. We are calculating an uncertainty in the best fit value of x half that arises owing to uncertainty in the position of the first sample mean, this being the one at x1, owing to uncertainty in the position of the second sample mean, this being the one at x2, and so forth. By reviewing the video tutorial on the quadrature formula, the viewer may notice that the entire process of obtaining a best fit value of x half by minimizing chi-squared is being regarded here as a so-called function. This is an example of how the functions abstractly referred to in the video on the quadrature formula can be presented in forms other than the one-line association rules introduced in the slide deck on algebra. The quadrature formula can still be applied even in situations where functions appear in the form of oral instructions or, for example, computer programs. In addition to the minimized value of chi-squared obtained from the yellow stars, we can obtain potentially different minimized values of chi-squared by fitting to the set of squares or instead to the set of triangles. Over a large number of experiments, we would get a large number of minimized chi-squared values. What is their average? Suppose that we are working with the fitting function that can be adjusted to coincide with the so-called correct curve. This is the curve upon which are anchored the Gaussian distributions from which the sample means were actually drawn. In this special case, the average of the minimized chi-squared values equals the number of measurements m minus the number of fitting parameters n param. In this case, sample means were obtained at x1, x2, x3, x4, and x5, so the number of measurements plotted is m equals 5. The number of adjustable parameters is n param equals 2 because we have allowed both x half and y naught to be adjusted. How can we understand the presence of n param in this equation? In the previous video, we calculated the average value of chi-squared after we sketched a single theoretical curve with confidence and without ambiguity. There were no fitting parameters. On this slide, however, we are not comparing datasets to a fully specified theoretical curve known to be accurate. Instead, fitting parameters allow an adjustable curve to float toward precisely those data points against which the curve is to be compared. This gives the minimized chi-squared value a tendency to be a little smaller than would be expected if the curve were the so-called correct curve, fixed in place by being pre-specified fully, that is to say, without fitting parameters. Thus, the average value of the minimized chi-squared across experiments is reduced from the number of measurements, as we will simply state without derivation here, by the number of fitting parameters n param. We denote the difference m minus n param using the Greek letter nu. This is called the degrees of freedom. The ratio of the minimized chi-squared value to the degrees of freedom is called the reduced chi-squared. Among those experiments and associated analyses in which the fitting function is constructed appropriately so that adjustments of parameters can allow the fitting function to coincide with the idealized or so-called correct curve, the reduced chi-squared is expected, at an order of magnitude level, to often take values in the neighborhood of unity. In this and the preceding video, we developed a familiarity with the quantity chi-squared and its use in choosing a curve that best fits a given dataset. In the next video, we write out an algorithm that students can use to apply this understanding in undergraduate introductory physical sciences laboratory courses.